the topics of this talk, I mean the whole course is divided into many parts. So, one is reaction rates and rate laws. Next, we will talk about effect of temperature on reaction rate. Then we will go on to complex reactions. After that, we will move on to theories of reaction rate, kinetics of some specific reactions, kinetics of catalyzed reactions. Then we will move on to fast reactions. After fast reactions, we will move on to reactions in solutions. Then some modern topics like ultra fast processes and last reaction dynamics. So, I am recommending these textbooks. So, one is Chemical Kinetics and Reaction Dynamics by Houston. Then another book is by Chemical Kinetics and Dynamics by Steinfeld, Francisco and Hess. Third one is Principles of Chemical Kinetics by House, and the other book is Molecular Reaction Dynamics by Levine. Now, apart from these books, any standard physical chemistry text will also help. Maybe many other books are available in market, so one can have that also. So, chemical kinetics, how is that important? Now, chemical kinetics affects everyday life. So, because it determines how fast insects walk, how quickly plants and animals grow, and even how fast hair grows on your head. And it is also very important in chemical processes. Now, selectivity and activity of chemical reactions determines how well chemical processes work. Now, in process chemistry, the important parts are like what reactions can lead to the desired products. Next is what side reactions can occur, and the third one is what are the rates of such processes that are occurring. Another important thing is reaction conditions. So, conditions like temperature, pressure, concentration, and catalysts are also important, and of course, solvents in which chemical reactions are carried out. So, these are very important, especially temperature and pressure. These are external factors. So, these are very important in chemical kinetics or maybe in chemical processes. Now, if we think of thermodynamics versus chemical kinetics. Now, in chemical reactions, in case of chemical reactions, these reactions can be one of the following. First one is not thermodynamically favored, maybe it is called as reactant favored. Next one is thermodynamically favored, which is also called product favored, but not kinetically favored. That is a slow reaction, that is the kinetics of the process is slow. That is why it is called kinetically disfavored, that is slow kinetics, that is with time it is happening slowly. And the third kind is thermodynamically favored, that is product favored and also kinetically favored, which is fast. That means it is thermodynamically favorable as also kinetically favored or kinetically allowed or kinetically very fast. Now, thermodynamics talks about feasibility of a reaction, that is whether the process, that is the chemical process, is energetically feasible or not, and kinetics talks about time course of chemical reaction, that is with time how is the process occurring, that is whether it is occurring fast or it is occurring slowly. Now, reaction rate is the change in concentration of one reactant or one product with time. It is generally defined in this way. Now, suppose we have got a chemical reaction like C is being converted to D. So, that is a C to D transformation. So, if we look into time rate of change of concentration of C, then we will write rate is equal to delta, that is differential quantity delta C or dC dt with a negative sign. Why with a negative sign? Because C is reducing in amount, and in the same way, if we think of the time rate of formation of D, then rate will also be written as del T of D. So, this is also rate, this is also rate. So, this is time rate of depletion of C, and it is the time rate of formation of D. So, where delta C is the change in concentration of C over a time span of delta T. In the same way, it is the time rate of change of concentration of D, although it started from 0, because at 0 time there was no 0, I mean there was no D, and with time D is increasing in amount. So, we can call that this delta D is the time rate of, I mean delta D delta T is the time rate of change of concentration of D, that is delta D is your change in concentration of D over time span of delta T. Therefore, since C is decreasing in concentration, therefore, it is a negative sign. So, we can write rate is equal to minus of del T of C, which is equal to del T of D. Remember this negative sign, it is here plus, this is a negative sign. Okay. Here it is a plus sign, there is no change in sign, but here is a negative sign because it is decreasing in amount. Okay. So, therefore, we can express rate in both ways, in terms of one of the reactants or maybe in terms of one of the products. So, let us move on to our next slide, where it is basically your the same reaction we just have talked about is your C to D. Okay. So, rate is equal to minus of del T of C, which is equal to plus del T of D. So, if we plot concentration of C and D together, I mean in the same graph paper as a function of time, then your D will rise like this and your C will decay like this. Okay. So, it is C and it is D. Okay. Now, if we look into the slide, that is you see that there are 4 beakers shown over here, and you see that the first one is deep in color, then it is fading, it is still fade, and now the last one is having no color. So, with time you see that the color is changing, means color is reducing, that is it is a decolorization reaction, decoloration of a dye with time. You see, as time is passed by, the color is fading, and the reverse thing may happen, where suppose we are starting from an uncolored or colored substance, and in course of reaction, so if the color is growing, then opposite trend may be found, like it is colorless, then fade color, it is a little deeper and it is the deepest, or maybe still it will grow with time. So, let us talk about chemical reaction rate and stoichiometry. So, start with a reaction of this kind, where 2C is converted to D. So, that is 2 moles of C is reacting to form the product D. So, how should we write the rate of reaction? Rate will be equal to, of course, del T of C with a negative sign multiplied by half. Why multiplied by half? Into half, and also rate can be written as del T of D. So, why multiplied by half? Because 2 moles are reacting together to produce 1 mole of D. So, to take into account of this stoichiometry, we have to multiply it by 0.5, that is 1 by 2, because each 2 moles of C together is acting as a single reactant. Therefore, effective concentration of C may be regarded as C by 2, as if 2C, that is 2 moles of C is forming D. That means, it is a bunch of 2C, that is why we are dividing it by 2. So, in general, if we have a chemical reaction like alpha A plus beta B producing gamma C plus or delta D, or I should not write delta because I already have used delta. So, eta D. Therefore, rate will be written as if it is in the reactant side, if it is in the form of reactant, then we will put a negative sign. If we write in terms of product, then there will be no negative sign, it will be written with a plus sign or without any sign. That means, it is a positive quantity. So, that means rate will be minus 1 upon alpha del T of A, which is equal to minus of 1 upon beta del T of B, which is equal to 1 upon gamma del T of C, which is equal to 1 upon eta del T of D. So, that means, you see that this alpha, beta, gamma, eta, these are all stoichiometric coefficient, and this minus sign is for the left hand side, that is the reactant side, and this plus sign or without any sign is for the product side. There is another way we can write the reaction rate. Now, in most general representation, we can discuss a reaction rate as a function of extent of reaction. Extent of reaction means how many moles of reactant that has reacted. So, in that case, we can write, if this xi is the extent of reaction, then rate will be written in terms of extent of reaction as follows: d xi dt times 1 upon V. Because suppose if xi moles of reactant have reacted, then and if the total volume is V, then the concentration of your reactant that has reacted is, that is xi divided by V, that's why it is called xi dot by V. So, rate of advancement per unit volume, time rate of advancement per unit volume. Now, if we normalize it to concentration and stoichiometry, then it may be written as rate is equal to dNi by dt divided by nu I divided by V, which is equal to dCi by nu I by dt. So, where n is the number of moles, nu is the stoichiometric coefficient, C is the molar concentration of the species I. Now, let us move on to rate law. The rate law is the relationship between the rate of reaction and the concentrations of reactant or products raised to the appropriate power. So, consider this reaction alpha A plus beta B producing gamma C plus eta D. So, rate can be written as, say, these are the two reactants. So, if we in general write rate is equal to, or may be written as it is proportional to the concentration of A raised to the power mu and concentration of B raised to the power nu, because chemical reaction is, rate of reaction is found to depend on the concentration of reacting species. So, if we know how this rate is affected with change of concentration of A or with change of concentration of B. So, this is the relation which talks about how rate is proportional to A and how rate is proportional to B with appropriate power. So, rate is equal to some constant which is called the rate constant, then A to the power mu and B to the power nu. So, that means we can call that the reaction has order mu with respect to A and order nu with respect to B. So, order mu with respect to A, order nu with respect to B. So, what is the overall order of the reaction? Overall order will be sum of the two individual orders. So, that means overall order will be equal to mu plus nu. Now, let us move on to rate laws. So, these rate laws are always determined experimentally. So, it is nothing but an experimental fact. Okay. So, these rate laws that I have written over here. So, this is determined experimentally. That means you change the concentration of A or maybe you change the concentration of B and then try to find out or try to formulate a relation between the rate of reaction, that is rate of appearance or rate of disappearance of some substance as a function of time, and then you will be able to formulate such a relation. Okay. So, this relation means that is called your rate law. So, these rate laws are always determined experimentally. Now, order of reaction is always defined in terms of reactant concentration, not in terms of your product concentration, but it is always defined in terms of reactant concentration. Okay. So, you see that I have written this reaction in terms of order. You see I have written this mu for A, nu for B. So, A, B, these two are all are on the left hand side, and I have written overall order in terms of their individual contribution towards the total order. Okay. So, order of reaction is always defined in terms of reactant, not product concentrations. Okay. Next is order of a reaction is not any way related to the stoichiometric coefficient of the reactant in the balanced chemical equation. We have to remember this point, that we have got, say, a chemical reaction of this kind alpha A plus beta B producing gamma C plus eta D. Okay. So, a rate equation, say rate will be equal to, say, K, I have written earlier, A to the power mu and B to the power nu. So, you see, means what I mean to say by this, that order of a reaction order of a reaction is not related to stoichiometric coefficient of the reactant in the balanced chemical equation. So, this mu and alpha, or maybe mu and beta, or nu with alpha or nu with beta, there is no relation between them. These are unrelated. These are unrelated event, because you see that this order of a reaction, it is fully experimentally determined quantity. There is no correlation between the stoichiometric coefficient and this power. Okay. So, let us have an example, a concrete example, that fluorine in gas phase reacting with 2 moles of chlorine oxide ClO2 also in gas phase, producing 2F ClO2 gas. So, here you see that stoichiometric coefficient for fluorine is F2 is 1, ClO2 is 2, and FClO2 is also 2. So, rate is found to depend as follows: rate is equal to K times F2 times ClO2. Although you see that this ClO2 in balanced chemical equation, it has got 2 over here, but you see it is coming as first power. Okay. So, that is why there is no relation between this power and this numbers. In some cases it may so happen that it is an accidental correlation, but it has no physical basis. Next is let us move on to first order reaction. So, what is a first order reaction? Now, first order reaction is a reaction of this kind, that suppose A is producing products. So, rate will be written by the following equation: rate is equal to minus d dt of A, because it is depleting, therefore, it is a negative sign, which is equal to K A, that is rate is proportional to first power of A. Okay. So, that is why it is called the first order reaction, it is called the first order reaction. So, that means your rate constant K will be equal to, that is the dimension will be rate divided by concentration, which is nothing but it will be second inverse per second. Here A is concentration at any time, that is, we can write in this way: A is concentration at T, and A is 0 concentration at T equal to 0, that is at the starting point of the reaction. Okay. So, if we now integrate, we will be getting like this. Exponential, it will be an exponential function minus kT, or then if we move on to ln, then ln A is equal to ln A naught minus kT. Okay. So, you see that this is your starting concentration, that is at 0 time, when the reaction has not started, or just before the start of reaction, this is the concentration of your reactant, and this is at any moment of time. So, you see it is in negative sign, that means with increase of time this quantity will be decreasing. So, it is an exponentially decreasing trend. So, if we plot concentration as a function of time, then for the first order reaction we will be seeing, if we plot as a function of concentration of A, I mean with time, we will be seeing it is an exponentially decaying trend. Okay? So, for first order, it is an exponentially decaying trend. Now, if we plot, another plot can be possible. If we plot rate with concentration, it will be like this for first order. That is your rate, means here it is basically rate is proportional to concentration. That means rate is equal to some constant into concentration. So, slope will be giving you this k, that is this side rate, this side concentration. So, slope will be giving you k. Okay. Another plot, if we do like if we plot ln A, okay, and this side if it is t, then you have to use this equation ln A is equal to ln A naught minus k t. That means, if we plot this ln A with t, then it will have a negative slope with some intercept. So, that means it will be something like this. So, this will be your ln A naught, and your slope will be, slope is basically your, it is a negative slope. This is the slope that will give you your k, rate constant of the process. So, for first order you can have three plots, A versus t, concentration versus time, it is an exponentially decaying trend. Rate versus concentration, it will have just a linear trend, and it will start from the origin, because no concentration, that is no reaction. When 0 concentration of reactant, there is no reaction. And there is another plot, that is if we plot like this ln A as a function of time, then we will be getting this rate constant as also, that is ln A naught, that is logarithm of, I mean natural logarithm of 0 time concentration of A. Now, we will move on to another term which is called half-life, which is for the first order reaction, half-life denoted by T half. Okay. So, this is nothing but the time required for the concentration of a reactant to decrease to half of its initial concentration. Suppose we started with 1 mole per liter concentration, and suppose after some time the concentration becomes 0.5 mole per liter, then the time required to change the concentration from 1 mole to 0.5 mole is the half-life of the process, or the half-life of the reaction involved in such a transformation. So, we can write when A, that is AT, better to say AT at time t, is A0 or A naught by 2, then corresponding t may be written as T half. Okay. So, for the first order reaction, how should we incorporate this T half, or how should we calculate T half? Okay. So, in that case we can write ln let us go back to the logarithmic equation. Ln A is equal to ln A naught minus kT. So, A will be, as per our requirement, A will be, this A will be A0 by 2. So, let us put ln A0, that is A naught by 2 is equal to ln A naught minus k T half. Okay. So, from this we can write, T half is equal to ln A0 by 2 divided by k. Basically, this is equal to ln 2 by k, which is nothing but equal to 0.693 by k. So, you see that for the first order reaction it is 0.693 by k. So, this happens also in case of radioactive disintegration, where the process occur via your first order kinetics, that is the radioactive disintegration occurs via first order kinetics. So, a typical example for such a first order process may be like decomposition of your H2O2 to water plus oxygen in gas phase. So, this follows a first order kinetics. So, first order, it follows a first order kinetics. So, that means T half will be whatever k will be getting, that will be used in this way 0.693 by k. So, if we can measure T half, then it is possible to find out this k. That means T half means the time required for the concentration, initial concentration of H2O2 to decay to or to reduce to half. That time is here, you will put that value, and then right hand side will be 0.693 by k. So, k will be equal to 0.693 by T half. So, k will be equal to 0.693 by T half. So, in this way we can also find out the rate constant. Okay, so now we will move on to second order reaction. Okay, so we have just finished the first order. Next, we will move on to second order. So, for second order reaction, typically your rate equation will be like A giving rise to products, okay. So, it is a second order reaction, okay. So, rate, very simple, you can write rate is proportional to say concentration of A to the power 2, okay. So, that means rate will be equal to k into A square. Now, rate is nothing but equal to, this is nothing but equal to minus of del T of A, which is equal to k into A square. So, it is a simple second order reaction where the same molecule of A is taking part, okay. There are examples where say A plus B giving rise to products, and that is found to follow a second order kinetics, that is also there, but it is a simplified case, okay. So, that means this is the rate equation, okay. Now, K will be equal to rate divided by A square, that is your mole per second divided by mole square, that is 1 by, it will be 1 by mole second. Of course, per liter is there always, okay, because concentration has got mole per liter. So, mole means mole per liter. Now, if we integrate this one, if we integrate this differential equation, we will be getting 1 by A is equal to 1 by A 0 plus K T. Okay. So, recall your first order kinetics. So, what we got there, that it is basically an exponentially decaying kinetics, that means A is equal to A 0 exponential minus K T. So, there is a huge difference in terms of your this integrated equation. Okay. So, there is a huge difference. So, we will discuss how this plot will look like. So, this is your concentration at any time, this is your 0 time concentration, that is when t equal to 0, that is at the start of the reaction. Now, if we think of the T half, then how should we calculate T half? That is when t is equal to T half, then your A is nothing but A 0 by 2. Okay. So, from this we can write that T half is equal to 1 by K into 1 by K into A 0. Okay. So, T half, you see that T half is inversely related to the initial concentration of the reactant. Now, let us move on to plots. For a second order reaction, the integrated equation is like 1 by A is equal to 1 by A naught plus K T. So, if we plot now, like concentration versus time, it will not be an exponential, rather it will be something like this, okay, some kind of hyperbolic nature. So, it is a second order. Okay. So, you can have a look at the slide also, and if we plot rate and versus concentration, then it will be, there is a growing trend. So, it is growing up. Okay. So, typical example could be, it is a typical example, CO gas plus Cl2 gas producing Cl2 gas. So, this follows your second order kinetics. Okay. So, for you see that for your first order case, it was an exponentially decaying trend, but here it is not an exponentially decaying trend, but it is a hyperbolic dependence, or maybe it is not an exponential one, it is something different, as if we look into this graph. And also rate versus concentration, if we plot rate versus concentration for your first order, it is a straight line like this for your first order it was straight line, but you see it is growing up, it is an upward curvature. So, looking at the concentration versus time plot, or maybe rate versus concentration plot, we can in principle distinguish between a first order and a second order reaction. Now, a general second order reaction, that is A plus B producing products. Okay. So, general second order reaction means your rate will be equal to, or I mean proportional to, concentration of A, concentration of B. Although I have started with a discussion where your second order reaction was a simple case where rate was proportional to, say, concentration of A whole square. Now, we have we are talking about rate which is proportional to product of concentration of A and concentration of B, and in both cases their power is 1. That is why it is a second order kinetics. So, your rate equation looks like this dx dt, that is x, if the concentration of product is x, then dx dt is equal to k2, because it is a second order reaction, that is why I have written k2 a b. Okay. So, then I can write k2 times a naught minus x, where this is your amount of product that is formed, okay, and this is your initial concentration of A. So, therefore, this much, that is a naught minus x, is the amount of A, I mean concentration of A remaining. In the same way, B naught minus x is the concentration of B that is remaining at a certain instant, okay. And upon integration we end up to this expression like this, okay. And finally, if we finally modify it properly, then it looks like logarithm of A by B at the instant of t, which is equal to 0.43, then rate constant times A naught minus B naught into t minus log B naught by A naught, okay. And this B naught and A naught, that is B 0 and A 0, these are the constants, okay. So, that is why if we plot the left hand side as a function of t, I mean x axis t, y axis log A by B, then it will be giving you a straight line, and the slope will be giving, means from the slope we will be getting your rate constant, okay. So, this is a general second order reaction. For this we can write like this. What about third order reaction? Still third order reaction is a possibility, that second order reaction, for second order reaction to happen like say two dissimilar substances, then according to the latest theory of reaction rate, we can say that there is a requirement of collision between A and B to form the product, okay. So, that means for a two body collision, that is A and B, collision between A and B, it is possible, but suppose a three body collision, that is you have got one particle over here, another particle over here, and the third particle over here, and these three particles will meet at one point at the same time, is a very rare event. That is why third order kinetics, for which three body collision is a requirement, and now such molecular reactions are very rare, although catalytic reactions do need a third component. And in that case, for a third order kinetics, your rate expression will look like this. For a general third order kinetics, the rate expression looks like this, that is dx dt is k3, 3 is for the third order kinetics, A, B, C, and this is concentration of A after certain time t, it is concentration of B after certain time t, and concentration of C after certain time t. What about nth order reaction? It is a general expression. So, if we consider only one reactant, that is only one reactant producing product. So, say A product. So, in that case, for a general nth order reaction, rate will be equal to K to the power n, that is nth power. It depends on the nth power of A, that is minus dCA dt is equal to K Ca concentration of A to the power n. Okay. Now, n can be integer. In certain cases, n is found to be fraction. I will come to this point on the fractional value of n. Okay. So, that is a special case, that is fractional order, and certain cases it is found that reaction is following a fractional order, although stoichiometry is not fraction, but reaction is found to follow the fractional order. So, that is a separate issue, but right now when n is now, if we concentrate on to this expression, then when n is not equal to 1, that is not for the first order case, and if we think that n is not equal to 1, and if we integrate the expression, upon integration we get this expression n minus 1 times 1 by Ca to the power n minus 1 by Ca 0 n minus 1, which is equal to Kt. Okay. So, if n is equal to 1, then this will have no meaning. That is why when n is not equal to 1, that is the requirement, we can integrate this expression. So, what are the features of this nth order reaction? Now, the unit of K will be like mole liter inverse to the power 1 minus n second inverse, and also if we plot this as a function of t, then this together will be giving you a straight line. That is, if we plot this in y axis and this in x axis, then this plot will be a straight line. Okay. So, with time it will follow a straight kinetics. Okay. So, if we plot here this one and this one over here, then it will be a straight line. Okay. And T half will be for a general nth order reaction, T half will be equal to 2 to the power n minus 1 divided by n minus 1 k into Ca 0 n minus 1. Of course, n is not equal to 1. So, you see that for the nth order reaction, it will be proportional to 1 by the initial concentration of the reactant raised to the power n minus 1, that is T half will be proportional to 1 by Ca 0 n minus 1. Okay. So, this is the T half value for a general nth order reaction, of course, when n is not equal to 1. Otherwise, if n is equal to 1, then again we will have a problem, that it will be meaningless. Now, let us move on to an interesting thing which is called the zero order reaction. So, what is that? A zero order reaction? Zero order reaction. So, reactant, product, okay. Rate, let us write rate is equal to minus delta T, that is equal to K rate constant times A to the power 0. So, this means equal to 1 effective. So, that is equal to K. So, that means rate is independent of concentration of your reactant. Okay. So, that means in that case K will be rate divided by A to the power 0 moles per second. Okay. So, that means if we integrate this expression, we will be getting A is equal to A naught minus K T. So, that means this is at any time t, this is at time 0. Okay. So, then what is the value of T half? So, T half will be equal to A 0 by twice K, A 0 by twice K. So, you see that it depends on the first power, it depends on the first power of A. So, recall a general general nth order reaction where we have written T half is proportional to 1 by C A 0 to the power n minus 1. So, if we put n is equal to 0, then this part will move on to over here, that is why T half is proportional to this. I mean these two match quite well. Okay. Now, if we have a plot of like concentration versus time, then for a zero order reaction it will be like this: rate versus concentration, it will be flat zero order. Okay. So, typical example will be decomposition of ammonia on tungsten or gold surface at an elevated temperature are the examples of zero order kinetics. So, in summary, what we have learned up to now, that kinetics deals with how fast a chemical reaction proceeds with time, and but thermodynamics talks about the feasibility. So, although in certain cases it has been found that certain substances are thermodynamically unstable, but it is found that they are still existing. It is because of the fact that they are kinetically stable, means their reactions are very slow, and in other cases some substances are found that they are, although thermodynamically stable, okay, but kinetically unstable. That means that substance is also undergoing reaction very fast. So, that means although thermodynamic stability is good, but kinetic stability less, means it is reacting fast. Thermodynamic stability less, kinetic stability high, in that case the reaction will also, the substance will also stay. So, that is very important point. Now, we have also learned this rate laws. In this case, that we have seen order can be 0 order, first order, second order, and rate equations are like for 0 order rate is k, first order rate will be equal to k times a, second order k times a square, and their half lives are basically for 0 order it is proportional to the a0 to the power 1, for first order it is independent of a0, for the second order it is inversely proportional to the first power of a0. So, we learned these basic rate laws and their corresponding equation and half life. So, and also the importance of kinetics. Now, how this can be applied to further cases, and in next couple of in next couple of classes we will talk about other things, but in the next class we will talk about a little complicated reactions like pseudo order reaction, that is, although a reaction is second order, but under certain circumstance this substance may be appearing to us like reacting in a first order kinetics. So, we will talk about this pseudo order reaction and also how this reaction rates can be measured. We will talk about a little bit, or maybe a little in a little detail in next class. Okay, till then, goodbye.